Hello everyone and good day. My name is Ashleigh Chua and today I'll be presenting on my final year project topic, thermal pollution in Kuala Lumpur. First of all, I'd like to introduce what an urban heat island is. As a city develops, surfaces are paved and trees and vegetation are cleared. Cars, industry, and lack of airflow cause a city to heat up. And when it gets hot, we turn straight to the air conditioning. Very hot days can create enormous energy spikes, further bolstering the heat. Urban heat islands are where the temperature is high in overdeveloped areas. The difference is even more pronounced at night. Next, the impacts of urban heat islands and global climate change are often similar. Increasing temperature from urban heat islands during summer affects the environment and quality of life. This phenomenon increases energy consumption, emission of air pollutants, it compromises human health and damages water quality. For the problem statement, urban heat islands degrade water quality with thermal pollution by affecting the metabolism of many aquatic species. Also, little to no research on thermal pollution in Kuala Lumpur is done via 2D simulations. Hence, I hope that my research will be able to contribute to this. For the objectives, the first would be to modify a surface heat balance model, which will be able to predict hourly air temperatures for Kuala Lumpur. The second would be to analyze the effect of building height, percentage of green area, and amount of concrete on urban heat island effect in Kuala Lumpur. And the third would be to investigate the feasibility of using the model for town planning purposes in cities with similar climate to Kuala Lumpur. Next, for my scope of study, I've chosen Kuala Lumpur City Centre as my scope of study. It is among the busiest areas in Kuala Lumpur with a high concrete mass, low percentage of green area, and high building mass, making it a suitable test area. For the methodology, first, I carried out literature review to establish a better understanding on the types of simulation. Second would be model selection. Ultimately, I decided to choose the 2D simulation. Third would be defining the input data, which represents Kuala Lumpur best. Fourth would be to test the model with the input data, and a software with an easy interface would be ideal. Fifth would be to define the parameters of study. 6, data analysis, and 7, proposal for problem solution. Next, a surface heat balance model is applied to the urban atmosphere. The model is expected to predict the correct order of magnitude of the urban temperature excess. I will then be using PTC MathCAD to solve up to 8 simultaneous equations. This is the basic framework of the model, where the energy balance is made onto a plane on the Earth's surface. The assumption is now made that the building mass is reduced to a homogeneous plane, which has no volume but can store thermal energy. These are the sets of simultaneous equations in which I mentioned earlier. In equation 2 and 3, highlighted in red, is the building height. In equation 6, highlighted in green, is concrete mass, and in equation 7, highlighted in blue, is percentage of green area. These are the variables which will be manipulated in the study. For input data, it encompasses air, soil, concrete, water, and other miscellaneous data. The data chosen is specific to Malaysian weather during the daytime at an average of 27 degrees. Next, I've come to the results and discussion part of my presentation. So in this graph, it represents the comparison of predicted and reported air temperatures. And for reported temperature, average data was taken for 30 days from the Meteorological Department of Malaysia. For the predicted temperature, it was obtained using the surface heat balance model in PTC MathCAD. For this comparison, the standard model is being used with a fixed evaporating fraction, known as the percentage of green area, fixed at 10%, the urban surface roughness, known as the building height, fixed at 5 meters, and average concrete mass fixed at 700 kilograms per meter squared. The deviation percentage from reported temperature and predicted temperature are relatively low, as only one reading exceeds a 10% deviation. Next, I'll be talking about the standard model results. First of all, I'd like to touch on the heat storage term. Heat transfer to a system is positive, and heat transfer from a system is negative. From the graph, it can be seen at around 3:30 p.m. The heat storage term dips below zero. This means that heat is released from the system to the surroundings. The heat storage further decreases till around 8 p.m. and slowly increases. At 5 a.m., the heat storage surpasses zero, which means the energy is absorbed from the surroundings. The heat storage further increases and peaks at 9 a.m. Next is the sensible heat flux to the air. This is the rate of thermal energy flow per unit surface area of heat transfer surface. Sensible heat is the heat that causes an object to change temperature. Next is the latent heat flux. Latent heat is the heat added to an object for it to change state. In the graph below, latent and heat fluxes is negative because the ground is cooling and water vapor is condensing, leading to a positive gradient in temperature and specific humidity. Last but not least is soil heat flux. And this is the energy received by the soil to heat it per unit of surface and time. The soil heat flux is positive when the soil receives energy. So next, I'll be talking about the sensitivity study of surface balance model by manipulating different parameters, such as the average concrete mass, the evaporating fraction, and the urban surface roughness. So first, I'll be talking about the sensitivity study of temperature by manipulating concrete mass. As concrete mass increases, the temperature profile tends to be more flattened, with the maximum temperature reduced and occurring in a later time. It can also be observed that the nocturnal air temperature is higher as building mass increases. This may be since a larger building mass requires more time to cool down. There is no lag when the concrete mass is little. The building mass is the least sensitive parameter as it only brings about a small percentage in the maximum air temperature. Next is the sensitivity study of temperature by manipulating building height. It is seen that the temperature decreases with increasing building height. This indicates that the increase of building height will bring a significant cooling effect in this height range. As the building's height increases, its effect on temperature is weakened. This is due to the influence of building shadows, local wind disturbances, and layout of buildings. Also, the nighttime temperature is lower as building height increases. Next is the sensitivity study by manipulating percentage of green area. The lag decreases slightly when green area percentage increases. However, the graph does not follow a smooth curve when green area percentage is at its extremes, for example at 0% and at 30%. It is seen that the graph does not converge at a single point. Hence, this parameter might not be suitable to test the surface heat balance model's accuracy. Hence, for the following discussions, I will not be including this parameter. Next is the sensitivity study of heat storage by manipulating both the average concrete mass and the urban surface roughness. For both comparisons of heat storage when building mass and building height are manipulated, the lag decreases when building height decreases and when building mass increases. Also, as seen in the first graph, there is no heat storage when there is no building mass. Next is the sensitivity study of sensible heat flux to the air by manipulating both the average concrete mass and the urban surface roughness. When concrete mass increases, the sensible heat flux to the air profile tends to be more flattened, with lag occurring later in time. When building height increases, the sensible heat flux to air increases. The lag decreases when average building height increases. Open space causes wind movement, which can transmit heat and humidity to the surrounding area, while density area causes the wind to be trapped in this area, affecting the air temperature. Next is the sensitivity study of latent heat flux by manipulating different parameters. So, as seen in the graph, when concrete mass increases, the latent heat flux profile tends to be more flattened, with a lag occurring later in time. Next, for urban surface roughness, the latent heat flux is the least when average building height is the highest. The lag also decreases slightly with increasing building height. Last but not least is the sensitivity study of heat flux into the soil by manipulating different parameters. First of all, The ability of soil to conduct heat determines how fast its temperature changes during a day or between seasons. When concrete mass increases, the heat flux into the soil profile tends to be more flattened, with the lag occurring later in time. For building height, the lag slightly decreases with increasing building height. However, during the night, there seems to be not much difference in heat flux into the soil regardless of average building height, and significant difference can only be observed during the daytime. In conclusion, when concrete mass increases, overall daytime temperature decreases, but nighttime temperature increases. This proves the effect of urban heat island. This is due to heat being stored in the concrete during the day and released during the night. The maximum temperature drop is 3.3 degrees when concrete mass increases from 0 to 1,500 kilograms per meter square. The effect of building height is also very significant for daytime maximum temperature, around 6.4 degrees Celsius when building height increases from 1 to 9 meters. Last but not least, the effect of green area percentage is also extremely substantial. The model predicted a whopping drop of 14.7 degrees Celsius of maximum daytime temperature and a drop of 7.1 degrees Celsius for the minimum nighttime temperature, when green area percentage increases from 0 to 30%. This basic energy model has worked satisfactorily for present city, but further studies in modeling and in more precise evaluation of input parameters should be pursued. Thank you so much for listening to my presentation. I hope you enjoyed it.